Ohio, Minahel. Good morning, all of you. Tom, that was a spectacular condensation of my talk in Kyoto and much more understandable. I am impressed by how much you were able to condense into such a wonderful short introduction. Thank you very much. And now I'm free to talk about an entirely different subject. So if I may have the first slide, this is my title, and I'm going to focus on what revolution occurred in crystallography that earned the Nobel Prize for Dan Shechtman, but I also want to show that periodicity and quasiperiodicity went from crystallography into the arts, architecture, design, and now we have a new tool, quasiperiodicity, to enlarge what we can do. So here's the prologue, and that's something I just added this morning. How did I get into rapid solidification? In 1970, my PhD student, Jim Baker, demonstrated that solute trapping occurred, and there had been a rule of thermodynamics, supposedly based on thermodynamics, which made this impossible, but it was not based on the correct principles of thermodynamics, and suddenly we had an enlargement of what could be achieved in theory by rapid solidification. And when 10 years later at NIST and National Bureau of Standards, I'd left teaching, I began a program of rapid solidification processing in the hope of making something very useful. And there was always great fear that anything that you made by rapid solidification processing would be unstable, and all kinds of terrible things might happen, or good things, depending, but it needed to be investigated. And so we needed an electron microscopist. And 10 years earlier, I had met a graduate student in Israel, Dan Shechtman, who then had done some work on solid titanium, no knowledge in rapid solidification or in liquid, but we needed an electron microscopist, and he was ready for his first sabbatical. And Israel gives 2-year sabbaticals. So he came to NBS for the 2 years, and he was so successful and in so many different projects that he came for years afterwards, every summer. Well, Robert Schaefer of NBS was exploring aluminum manganese alloys, and they were the opposite of the alloys that Jim Baker and I had explored. So they were at the opposite end, very little segregation on solidification, and so there was no trapping, but he wanted to test some other aspects of the theory. And Dan Shechtman was helping him identify what crystals he was making. And then they decided to go to more and more concentrated manganese solutions. And all of a sudden, Dan Shechtman, one morning in 1982, saw this diffraction pattern. Now, the sharp diffraction spots indicate that there is a great deal of order, that there are planes of atoms in the material that diffract, that are spaced at recurring spacings. So that was fine. That's what crystals do. But this particular diffraction pattern had a 10-fold symmetry. And it's actually a 5-fold rotation. That is, if I put an axis through the center here and start rotating, if I rotate by 36 degrees, it looks exactly the same. That's called a 10-fold rotation. It's actually only a 5-fold rotation, because we're seeing things from the back. Here is a pentagon in a transparent polyhedron, and on the other side is a pentagon in the opposite direction. That gives you a sort of false impression that it's tenfold, but tenfold isn't allowed either by the rules of crystallography, and neither is fivefold. So by rotating the specimen in the electron microscope to different orientations and measuring how far he rotated, he got the original fivefold, and if he rotated in one direction, this is a twofold, this is another fivefold. In this direction, there's a threefold, which looks like a sixfold, but it's only a threefold, a twofold, and a threefold. And of course, these diffraction patterns are now, because this is a thin foil, and if you rotate it enough, it doesn't give you a nice thing, but it's still clear enough that these are the rotations. Well, that's a familiar, this is the icosahedral symmetry. It's, if you look at your soccer ball, you will see that symmetry. And in Japan, I was given this lovely ball. Here is a pentagon. This is a fivefold axis, goes out through here. If I move in this direction, here is a twofold axis if I stick a pin in there. And here's another fivefold axis. Here you go from 5 to 3 to 2 to 3. And the angles that were measured were exactly the angles that are predicted. This is a stereosgraphic projection of all of that, and here's a magnification of it. Here we have 5, 2, 5, 5, 3, 2, 3. Here is a dodecahedron, 5, 2, 5, 5, 3, 2, 3, and then back to 5. Here is an actual crystal done much later of this kind of this phase, but with different materials. Here you go from 5 to 2 to 5, or 5 to 5, and 5, 3, 2, 3. So this is clearly an icosahedral symmetry. Well, it's forbidden by the laws of crystallography. A theorem of crystallography, the diffraction pattern of a crystal has essentially the same rotational symmetry as the crystal itself. That holds true for this crystal as well as any other crystal. The crystallographic restriction, and this is the thing that's violated, the rotational symmetry of a lattice can only be 2, 3, 4, and 6-fold. Notice I'm not saying here crystal, I'm saying lattice. So crystallographers had assumed that there is a lattice associated with crystals, a periodicity, and this does not allow 5, 7, 8, 9, 10, and so on. Therefore, crystals are forbidden to have one fivefold axis, let alone 6 of them. Well, when a law is found wanting, what do you do? And let me first of all say that there are laws which are based on very, very fundamental things, and then there are laws which are created by humans and not based on fundamentals, and sometimes we lose track of that. So here's the first and second law of thermodynamics, and oops. Even Einstein said those laws will never be overturned, and then he said, skeptics note. So violating a law of thermodynamics, you don't even bother. You're not going to do it. Now, Newton's laws of motion is a good example of something which was not based on fundamental laws, but it certainly worked, and it works for hundreds of years without exception. And then came along quantum effects and relativity, and they had to be amended. But it didn't destroy Newton's laws. We still, in engineering, use them. We just have to watch out when when the bodies start going too fast or we're dealing with something too small. So here was a major revolution that didn't overturn Newton's laws, but it just said there are limits at which point you have to go to something else. Well, here is the crystallographic laws are based on periodic arrangement of atoms, and that law forbids five-fold rotation. But here it was, so you can't get away from the experiment. Here was a crystal which had that rotation. So there had to be a revolution, but whatever happens, most crystals don't have a five-fold rotation. In fact, almost all didn't, and therefore crystallography was still intact for them. But when there was a five-fold rotation, or 7 or 8 or 9, then we had to deal with something new. Well, it took 2 years for Dan Shechtman to get brave enough to publish this, and we did publish it, and there were 3 of us who joined him, myself, Denis Gratias from France, and Ilan Blech from the Technion. It was amazing. It was accepted immediately at a very tough journal. Physical Review Letters rejects, I think, 80% of the papers that are submitted. But when it has something, it's peer-reviewed. We submitted it 9th of October. It was published 5 weeks later. It was immediately accepted. The data were compelling. Something was wrong, but you don't argue with an experiment that's well done and has all the convincing data with it. So that is it, and then all hell broke loose. The small group of us at NBS that have become NIST that were working on quasicrystals, suddenly we got 300 manuscripts sent to us in the first year. Now, that's 1 a day, and they were difficult. We didn't quite understand what these crystals were. We didn't quite understand, but we had found them, and we had the data to prove that it was there. So awards came quickly to all authors. In fact, Dan Shechtman was an invited speaker at the March meeting of 1985. So within 4 months of publication, he was invited speaker at a short symposium of 13 submitted papers. And so the structures were named quasicrystals, and this was done by Paul Steinhardt, because he identified this periodicity as a quasiperiodicity. And this is something we had never heard of before, but we suddenly realized that what we had was a quasi-periodic crystal. It was a crystal, but it didn't have a regular periodicity, and this was something that turned out to have been studied by mathematicians since the 1890s, and by 1930 it was a finished subject. It was a curiosity. Nobody was picking it up, but it was there, and all the math had been done. This is one of the wonderful things about mathematicians. They would pick up odd things like this, and decades later, when you need it, it's all there. It really was very helpful. But there was noisy opposition, and there were alternate explanations, particularly saying large unit cells. Well, what's the difference between a large unit cell and an infinite unit cell? You can't experimentally distinguish between that. But they also thought that these quasicrystals were made up out of crystals, real periodic crystals, but sort of many small ones all fit together to give five-fold symmetry, and I'll talk about this. And why were they so angry? You know, because it's all over with, and there was no reason for them to be angry. But scientists, when they have laws that they love, they get angry when they're threatened. So here, and most of the stuff was carried out in the newspapers rather than in the, and we never bothered to answer to them. But, you know, cold water on icosahedral symmetry towards five-fold symmetry, puzzle crystals plunge science into uncertainty. This kind of stuff, you just don't answer. I mean, you try to stick to the published publications, and we were getting lots of confirmation, so we thought this was all nonsense and would go away. But the main person from who was really no longer a scientist, but knew how to do political things. I mean, he published statements that are saying, crystallographers, I've looked into this, crystallographers can go back to their labs because their theories are intact, this is all nonsense. And now, that is something which worked very well for crystallographers. So most of the research was done by physicists and mathematicians and material scientists. The crystallographers in this country were reluctant to enter a field like that. And this is in part because crystallography was a very mature science. And I'll talk about that. Anyway, the big thing is the Nobel Prize came last year to Dan Shechtman, this fellow here. And here is the team. And I'm happy to say that Leo Bendersky is here today, and Frank Gale and Carol Handwerker, who were new to this, so they were too young to be part of this. But there's Denis Gracias, there am I, and there is Frank. And here are the earliest electron micrographs at the atomic resolution that showed that there are planes of atoms, but they are irregularly spaced. In fact, they have two spacings, and the spacings come at irregular intervals. And that's characteristic of quasiperiodicity. Okay, now that's the prologue. Here comes the actual talk, an introduction to periodicity and its currents in science, music, and art. And then what the crystallographers believed, which was a 200-year-old hypothesis that, just like Newton's law, had had no exceptions and therefore became a law. And earlier exceptions could be subsumed as defects. I mean, if you have an alloy, it is not, you have different atoms in different unit cells. So there is no periodicity in an alloy, unless it's very highly ordered, which occasionally happens. But you could subsume this disorder as defects, and then you were left with if you ignored the defects, if you ignored the disorder, you had something that was periodic. So in every case here, you could see the underlying lattice. But quasicrystals could not be subsumed. There was no way of turning that into a lattice. So it required a new hypothesis, and then I'll finish with an introduction to quasiperiodicity with the new emphasis in mathematics, science, music, and art. Okay, let me define periodicity. You can move from one spot to another, and it's an identical place. It's an identical place all the way out. It's not just the immediate neighborhood, but as far as the eye can see, it's an identical place. So that's periodicity, and going from point to equivalent point puts in a point lattice, and the distances that you move from point to point are translations. Rotations is turning a structure about an axis to see if it superimposes identically on the unrotated structure. The number of this, when I say sixfold and so on, the number of repetitions to go a full circle is what it is. So if it's a sixfold, it takes 6 repetitions before you get back fourfold, twofold, even onefold. That is, for structures, onefold occurs. And then there are mirror planes when a reflection superimposes identically, when reflections superimpose identically on each other. So those are the limites. Now, the important thing, and this is very important for crystallographers, symmetries reply repetitions, and therefore they impose constraint. That is, once you have decided that this is going to be, it's going to have this symmetry, you have no freedom when you go from one place to the next or when you rotate. It's got to be identically the same. So it is a real strong restriction on what is possible. And so you know what is or is not possible. And this is both helpful and frustrating. If you don't know what is going on, it's very helpful to have a limited number of possibilities. You can go through them, even though there may be hundreds, but that's it. There are those and no others. Or it can be frustrating. If you want to break out of those restrictions, then opportunities come out. And so therefore, laws like this law of crystallography or Newton's laws, when you break out of them, you discover that they were not the laws, that they had exceptions, and you have real revolutions, real opportunities. So now many symmetries are based on experience, that aesthetics, customs, and rules, and those are open for strict adherence, and they create opportunities when there is an artistic revolution. You know, when some modern way of doing a painting, which before was not considered a painting, now suddenly you have a revolution. They're also revolutions, but you're not breaking any law. You're just breaking something that is based on custom or aesthetics. Okay, let me talk a little bit about repetition by moving, rotating, and reflecting. Consider this to be an infinite checkerboard. Now, I have fourfold axis at the blue diamonds, and there's a different fourfold axis on each. If I rotate about that point, it superimposes on itself. There is a twofold axis here. If I rotate by 180 degrees, the black comes up to here and the white comes back to here. So this is also a symmetry. There are mirror planes through here, through here, through here, the diagonals, through the whites, through the blacks. They're all mirror planes. So there's an awful lot of symmetry, and therefore an awful lot of restrictions if you want to keep this symmetry. Well, let's show where the lattice is. See, I now put the point lattice at every white corner, and this is the lattice. But I can move the lattice because it's periodic with all the restrictions. If I move it, so I now moved it from the white to the black, it's still a lattice. Or if I decide to go to corners, it's also a lattice. It goes from the same place to the same place, and crystallography recognizes this as a different place because here the blacks are this way, here the blacks are that way, so this is not the identical place. So it's one lattice, and it can be placed anywhere. Well, here is the beauty of periodicity. This is what is so wonderful about the aesthetics of periodicity. This is the checkerboard. Let's make this the fourfold axis of the white. Here's the fourfold axis of the black. Here is black, black, black along the diagonal. Here is white, white, white. Here is black, white, black. This is the checkerboard. And here's a mirror. Here's a fourfold axis. There's a fourfold axis. Here's a twofold axis. Rotate a twofold. Here are mirrors this way. And all the symmetries are preserved. This fellow that did this for the Alhambra took full advantage of all the symmetries, and it made his task easy, and it makes the crystallographer's task easy. This is the triangle. Once he had designed this triangle, he had designed everything. He can just go around and reflect it or move it and so on. There's nothing new. So symmetry is therefore immensely helpful. And I'll show that same triangle here in the lattice. It occupies 1/8 of the unit cell. So if I pick a tile here, this tile is repeated 8 times. And in crystallography, in some highly symmetric crystals, an atom sitting on a site like that can be repeated as much as 96 times. There's no, if you want to keep that symmetry, there's no deviation from it. So, once the craftsman had decided this, he could turn this over to an apprentice, and the apprentice could make the entire wall. And this is wonderful for crystallographers, because with this kind of symmetry, they have only a limited number of bands. Now here we've kept the lattice, but now we've put in molecules, winged horses, and they have no symmetry at all. So we still have the translational symmetry, white, white, white. We have a lattice, but there's no place where we can rotate. So a motif put into a lattice can only reduce the symmetry. It cannot increase the symmetry. And here is the lattice. Since there's no special place, I put each point on the belly of the red horse, and it works just as well. So, okay, now we come to tilings. And this is the easiest periodicity to understand. 1, 2, 3, 4, and 6-fold symmetries are easy and were plenty throughout history. Most attempts to construct periodic tilings with 5, 8, 10, and 12, and by the way, we now have quasicrystals with 5, 8, 10, and 12-fold axes. Leo Bendersky is the discoverer of the first one with a 10-fold axis, and he's in the audience today. We're unsuccessful. So it was long known that these are not possible in periodic tiling, but we've recently discovered that 13th century Mooring tilings had 5- and 8-fold symmetry. That's Moors, in North Africa and the Islamic world, they were way ahead of us, because Dürer in 1525 and a year later, Kepler tried to find the impossible periodic tiling with 5-fold symmetry. And in the West, aperiodic tiling became a research topic, and we have the famous Penrose tiling. Today, all rotation axes are easily generated with quasiperiodicity. So here is an attempt to start tiling triangles, squares. You can just keep going. Pentagons, regular pentagons, that is, a regular tiling requires regular pentagon, leaves a gap here. But you can fill it in, and when you put it together, you have a crystal. You have a periodicity, and it is a unit cell, which is sort of an elongated rectangle with a lattice point in the center. So this is a periodic structure. And here is, when you make the hexagons, the bees know how to make a lattice. And here is the defects. This is from my hometown, and this is the most awful lattice. I mean, the periodicity, there's so many defects. But yet, when you're finished, you say, aha, there is a lattice here. It's a rectangular lattice, so many blocks to the mile north-south, so many blocks to the mile east-west. And every once in a while, things are missing. Here they're very close together. Here they're further apart. But this is what crystallographers have done. When they have a defective crystal, they would ignore the defects and find the lattice and say, aha, we have a periodicity. So, okay, now we've taken this Albrecht Dürer thing, magnified. You can see here is the rectangular unit cell with the lattice point in the middle. And look, he filled it out to cover the entire space. So if I say I'm going to have pentagons and wedges as two kinds of atoms, I've made a crystal. And here the crystal seems to have fivefold symmetry, tenfold actually. Every pentagon is in two orientations, pointing up or pointing down. And it's true everywhere that pointed down or pointed up, pointed down or pointed up. So there's only two kinds of pentagons. The white things are different orientations, but there is no lattice. There's no place where you can go and pick a unit cell like you do here and just extend it over the entire domain. And there's only one point of fivefold symmetry. So what's going on here? This is the only point of fivefold symmetry. What's going on here? There. Now, Leo Bendersky kindly colored this for me. You have 10 crystals in wedge shapes that fill the space. Each crystal is periodic. Each crystal has its own orientation. And the whole pattern is fivefold. So this was one of the suggestions that Pauling made that we had. But that's so easy to detect because you can go to a diffraction pattern out here and you have a crystal, or out here you have a different crystal. Or if you do the whole thing, you have a superposition of the diffraction pattern of 5 crystals. So that clearly was ruled out experimentally. Here is Johannes Kepler trying to, 100 years later, trying to make a fivefold pattern with lots of different things, pentagons and decagons and so on, and stars. Here he has, whoops, here he has a center, which is fivefold symmetry. Here is a center, but it no longer really has fivefold symmetry. And by the time you get out to here, it definitely doesn't. And when you get out to here, you don't even know how to fill in anymore. Whatever rules he had for what neighborhoods occurred stopped. So, but he did a very important thing. He did an atomic basis of symmetry for snowflakes. Now, it was very logical for people to, when they saw crystals, and they could fracture the crystals and cleave them, to assume that crystals were made out of molecules that had the same shape as a crystal. And that just repeated. But he showed that a bunch of balls could make snowflakes. And this was one of the early attempts to understand hexagonal symmetry as a basis of it. Well, here is a tiling, a Moorish tiling from a century before, 1323. It's just being published this year by Ajluni, Quasiperiodic Islamic Patterns, and it's going to appear in Acta Christ a little bit later, and she kindly gave this to me. Here is a higher symmetry here. Here is from 1270 a stone, Suleiman stone in Iraq, circa 1270, which Denis Gracia sent to me. This is eightfold symmetry, which is another forbidden symmetry with defects, but it is continuing. It is quasi-periodic with defects. Here are the famous Penrose tiles, and these are now commercial. You can buy these tiles and put it on your floor or on your countertop. And here is a beautiful artistic example of quasiperiodicity. You see here you have a fivefold axis. It is repeated over here, but nothing is over here. You go from, well, I mean, whatever happens, you go from here to here, but the surroundings over here are different from what it is here. So these are not lattice points. There is no regular spacing. You have local regions, so it's highly ordered, but that's it. And, oops. Okay, now let's turn to crystallography. René Just Aoui, this fellow here, was a wonderful mineralogist, and he is responsible for breaking crystallography from the idea that the molecules had to conform to unit cells. He simply said it isn't necessary. They can be any arrangement, but they have to be the same periodically. And here is a demonstration that you can have from his paper, that you can have all kinds of crystal shapes from little cubes and so on. Well, this was a wonderful way of stating it, and he did a fair amount of his own mathematics, but mathematicians grabbed it. And so they created catalogs. Now, a catalog to a mathematician is every possibility, none left out. And so my Bible, and the Bible of crystallographers, is the International Tables of Crystallography. Today, it's completely generated by computers. It's 854 large, really large pages. It's heavy. And this is totally accurate and reliable. And it has every possibility for crystals on the assumption that things are periodic. So the old assumption is that the atoms of every crystal repeat periodically like a motif in an ornamental pattern. No exceptions reported. Well, the exceptions that were reported could always be subsumed. Then the theorem, crystallographic restriction, and I'll talk a little bit about that, and quasicrystals have no lattice. Okay, no possibility left out. Rotations, only 1, 2, 3, 4, and 6. That's all. Nothing else is allowed. Only 10 or 32 combinations of rotations. Now, a cube has 3-fold axes, 4-fold axes, 3 different 4-fold axes, and so on. So these kinds of combinations, there are only 32 possible, and these are the point groups. And they determine the directionality of crystal properties, and they determine the allowed crystal forms. Amazingly enough, there are only 51 forms for crystals. And that was wonderful for mineralogists through the 19th century. They could tell which point group they had by looking at the crystal forms. Now, translations, only 5 translations, only 5 lattices exist in 2 dimensions, only 14 in 3 dimensions. Then when you combine rotations with translations, you get only 19 plane groups and only 230. Now, only 230 sounds like an awful lot, but that's all. So this makes crystallography a very mature science. People learned this, and they operate with it with great confidence that there's never any exception. So they become technically superior. Today it's all handled by computers, but in the old days, this was it. And this made crystallography a very exact and mature science. And the kind of people who went into crystallography loved to learn all these rules and all the things, and they were then content that they never have to deal with anything else. And that was their problem. They did not see this as an opportunity to break out, and physicists and mathematicians and material scientists loved this opportunity. Okay, a quick, if things are periodic, then there has to be a shortest distance. And let this be the shortest distance, because if you can get to a shorter distance, eventually there's no distance, and then it's a smooth thing. So there has to be a shortest distance, and nothing could get less than it. If I have a 60-degree angle, this is a six-fold axis, and this is the right distance. Any axis greater than six-fold makes this angle smaller, and that makes this distance less, because remember, this is a lattice point, this is a lattice point. When you rotate by whatever that axis is, you create a lattice point here. Now two lattice points are too close together. Fourfold is okay. Fivefold is just a little bit more complicated. You can do this to that, and that's okay, because that's larger than D. But now this is a lattice point, so there's got to be a 72-degree rotation here, and now you have a distance which is shorter. That's all there is to the proof that fivefold is impossible. And now here are only 51 crystalline forms. These are the Platonic solids. These are the only 5 solids that have regular faces of the same size, regular pentagons, regular triangles, regular squares. There can be no others. Amazing enough, of these 5 basic forms, 2 are illegal. And I just want to point out that the octahedron and the cube belong to the same symmetry. Here, the fourfold axis goes from point to point. Here it goes through the center of a face. Here is the threefold axis is here. Here the threefold axis is the center of a face. The twofold axes go through the centers of the edges diagonally across. Here it does the same thing as through a center of an edge. So octahedron and cube are both cubic forms. And you know there's diamond salt and there is cubic salt. The diamond company has been growing sodium chloride in this form, and it doesn't stick together in moist climates. But here, this is a form, an allowed form. These are not. These are some possible forms, and these are impossible forms. You know, I didn't know it would do all that. And here is a quasicrystal. Now, I have, that's the dodecahedron. Frank Gale has made the icosahedron, this form, out of a quasicrystal, but I didn't get to copy it into this thing. Here, there are only 14 lattices in 3 dimensions. That's it. There ain't no others. And it starts from simple cubic, face-center cubic, body-center cubic, tetragonal, and so on. That's it. There can't be any others. Well, here are the 17 plane groups. And the Carpet Museum in Washington, D.C., not the Carpet Museum, the National Museum of Textiles, published this. And here is the horses. I mean, F is an asymmetric unit, so you create symmetry by putting F's into different proportions to other by rotating. So here are the horses. Here's the Dura tetragonal. I'm sorry, rectangular. Here's the checkerboard. Here is the honeycomb. And so here are 4 of the possibilities, but there are 13 others. And Escher published a book where he for the crystallographers, where he created a pattern for each of these 14 ways of having periodicity. So isn't it wonderful to have such a limited catalog if you are making carpets? But fortunately, carpet makers have freedom to deviate from this. Here is the properties depend on the symmetry. I just want to show one birefringence. Calcite light goes into 2 directions when it goes through, so if you see the letter here, there are 2 letters there. This is a property of the particular lattice. Symmetry may restrict light to only go in one direction, in which case you don't have this. Okay, 20th century was a revolution in crystallography with the X-ray, and later on with neutrons and electrons, and our pattern was done with electrons. Crystals become defined by their periodicity because diffraction requires periodic layers or quasi-periodic layers of atoms. And so now we can study disorder and defects. And here is the classic paper that won a Nobel Prize, where the X-rays come in, they diffract from the atom layers, and here are spots very much which tell you where the layers are and how far apart they are. So this becomes a very powerful tool in crystallography. And just to remind you that you can take a disk and put it in sunlight, and the colors all get spread out. If I had only one color, which is what the electrons are doing, then we would have only the spot for that color. So instead of having a streak of a rainbow, it would be spots. Okay, here is a typical diffraction pattern of a crystal. This happens to be sodium chloride. Here is the quasicrystal along I think a twofold axis. And you can see it's very different. First of all, the spots here are also not regularly spaced. There are two spacings. Okay, what's quasiperiodicity? You're probably anxious to learn all about it. It's a very common thing. It is when there are more periodicities than there is dimension. And you know, the thing that comes first to mind is a pure tone is a periodic sound wave. But if I have two tones, then if they are rationally related, there is a periodicity. If I do harmonics, pure harmonics to a tone, the periodicity remains. But if I take two different tones that are irrationally related in their wavelength, then there's never any periodicity. So that's quasi-periodicity, and that's true in a lot of music. So it is a bit of an anharmonicity. I'll try to demonstrate it. The thing is that if I have, that's what we think the mathematicians about it. Let's forget about the dimension that's actually in. Let's go to a higher dimension. Then quasi-periodic becomes a slice of this higher dimension, and quasi-periodicity is aperiodic because these are independent wavelengths, but approximate dimensions on all size scales agree as the various periodicities beat against each other. You all know that if I beat two tones against each other, you get sort of a periodic up and down in the sound level. Now, higher symmetries are allowed because higher symmetries are allowed in the higher dimension. And so this is all that it is. And now that sounds terrible, but let me give you let's consider some simple cases. Here you are a mason, and the task is, here are the stones. They are rectangles. The task is to build a slope of this amount. You have an easy task. Nothing, you put up this line and nothing above this line. Every stone has to be below this line. So here we go from here to here to here. There's a step every time. Now, if the slope was this way, which is still rational, it's just 2 out of 3, you have periodicity. You go 2 steps, then you go up 1, then you go 1, and then you go up 1, and then you go 2 before you go up 1 to get this slope of 2 over 3. That's still periodic. But if I have these slopes which are irrational, then if this thing starts over here at a corner, it will never be exactly at a corner on either of them. And so what you have is something which repeats, but never periodically. But it definitely has the sort of characteristics where it alternates between 2 and 3, or 5 and 6, but never exactly. So that's quasiperiodicity in one dimension. Notice that this pattern is two-dimensional. The blue pattern is two-dimensional, and what we want to know is the path along that one-dimensional line. So that's quasiperiodicity. Now here is a little bit more complicated. Now this is a tiling of 3 different colors tiles. It's two-dimensional, but your eye immediately thinks it's three-dimensional. And that's much easier to understand this as a three-dimensional tiling that has been cut. I've laid a plane across this lattice, and I said no cube that crosses that plane, all the cubes have to stay below that plane, and this is what I get. Now, if that is a rational direction to the orientation, it will never repeat. But there will be a kind of a periodicity or something, or some kind of an order. And if you want to know how to get from one place to another, you decide, well, I'll do it in 3 dimensions. And to go from here to here, I go so many up, so many this way, so many that way. And that's unique. Doesn't matter what path I take. So it's uniquely defined because in 3 dimensions, it's all very clear. In 2 dimensions, it looks like, well, a quasi-periodic. Okay, so this is going from there to there. All right, you do the same thing here with Penrose tile. Now look here, that looks like a cube. But this face here is part of this cube. Well, this cube has a certain orientation of this face, but this cube doesn't. It has a different orientation. So it turns out that if you now lift it to 5 dimensions, which I'm sure you've never thought of before, you know exactly where you're going, because each step in one direction from lattice point to lattice point tells you which dimension it is. This is 1 dimension, this is the 2nd dimension, this is the 3rd dimension, this is the 4th dimension, this is the 5th dimension. So if you want to go from here to here, in 5 dimensions, there's no trouble. So there is a 5-dimensional lattice that is underlying this, at which point it becomes very simple. Don't try to visualize it, but just do it with algebra. Just determine the coordinates, 5 numbers for a coordinate of where you are, and every time you go in one direction, one of those clicks up, and then the next one. So it takes a while to get used to this, but then you take this 5-dimensional crystal, which is now perfectly periodic, and you slice it. And you slice it in a way that you keep the 5-dimensional, the 5-fold axis, because and so this is what you have then. This is the Penrose tiling. That's a much easier way to explain Penrose tiling than the way Penrose did it originally. He was a cosmologist, and I'm sure Dr. Sunyaev will understand that he proved that this was aperiodic by inflation. And inflation is, I think, much harder to understand than 5 dimensions. Okay, here is the same pattern, and here is walking, if you want to, but it is a 2-dimensional image. And now let's get back to quasi-periodic Moorish tiling. Not only this one that I showed earlier, here's a wall in Isfahan, Iran, which is a century later. And Ashlouni has figured out how you can make a pattern like this, whoops, that because it's quasi-periodic, you can make a pattern that you can now give to an apprentice. It is somewhat of an inflation, but now an apprentice can make this rather elaborate pattern, which never repeats, using that ruling. And of course, we don't know what instructions the Moorish tiler would give to making this kind of a pattern. Okay, quasi-periodicity in 1D is music on a time axis. There are patterns and borders. Here is from, again, the Textile Museum. There are only 7 border patterns if you insist that your border be periodic. These are the only ones, and this is a description of the fundamental design, but these are the 7 border patterns. Now, why would you want to be stuck to 7 border patterns? Well, these can be very elaborate, and that might be satisfying you, but if you want to break out, there is no problem. The crafts become very constricted, just like crystallographers. There are rules, and by God, this is what you do. So you go through the Carpet Museum, and you find these borders. Now, this is some modern borders, and people just, it's all one-dimensional. But whoever put these together didn't insist on the same periodicity of different stripes. So they were perfectly free to put in independent periodicities in each. So these are quasi-periodic. Of course, accidentally so, but why not use it? Why not do it? If you find some beauty in it, why not do it? So here now comes something that I'm not sure will work. Here is an ideal tone. How do I do that? Well, never mind. I put in some tones where things were perfectly in ratio, and it sounds dull. If I go to the equitemperament of Bach, we're dealing with the 12th root of 2, which is irrational, and it sounds much more interesting. And here are some scales, which I won't play for you, because I don't know how to play it here. It works on my computer, but not down here. All right, I'm running out of time. Here is something I was going to demonstrate. Morellet is a French artist, and he designs patterns like that long before there were quasicrystals or Moorish tiling. All he does is take square grids and rotates them relative to each other. Now, each square grid has 2 dimensions, so by the time you rotate 2 square grids against each other, you've got 4 dimensions. If you rotate 5, you've got 10 periodicities. And by God, so you get very interesting patterns. And I saw him in the Pompidou in '84. There was an exhibit of his art, and I immediately said, my God, what a genius. Here is quasi-periodicity, Penrose tiling in an American Indian blanket. So this is spreading to art. Here is mathematics. Now, this is coming up. I got this from the website. These are tilings. The left is a minimum Pisot number tiling. The middle is a Sophic Pisot tiling. The right is a Rousey fractal. I have no idea what it means, but I do see that this is a fractal because you can see that all of the spaces are self-similar. They get smaller and smaller and smaller, but this fractal pattern fits into a five-fold plane and can continue. So the Numeration and Substitution 2012 is the name of the conference. It's in Japan at RIMS. And the website says current favorite are these kinds of structures. So the field is alive in mathematics. Architecture, there was, before Penrose, there was an architect, Stephen Baer, who decided that he was going to build the space, build things using what we today would call three-dimensional Penrose tiling. He got them out of 6 dimensions. By the way, I should say that the quasicrystals are periodic in 6 dimensions. Every one of the axes is perpendicular to 5 of the other 6 axes, so there's a 5-fold rotation along each axis, so you have 6 5-fold axes, and so icosahedral symmetry is periodic in 6 dimensions. So architecture. Steve Baer is an architect who has been really active. Nobody wants to live in a quasicrystal house, though, so it's playground structures, toys and games coming out of his work. And he was really quite a genius, and his book on Zohm works specifically says he gets these structures by projecting from 6 dimension into 3. Then there are Penrose tilings, which not only have been for floors, but also for decorative window glass. And here is my physics building at the University of Washington. The windows at both ends of the stairwell are Penrose tilings. And this is a very, very nice pattern. It makes me feel good every time I come to work. Whoops. This is something which Denis Gracias has sent me. He now can computer generate any axis. And so here is an 8-fold axis, which is now being used by a designer, an octagonal designer in the old town of Abu Dhabi. This is under construction, and here you see 8-fold tiling as a window dressing. It's very attractive. I'm waiting for those scaffolding to come down. Okay, let me summarize now. The revolution has changed the definition of a crystal. If you go to Webster's dictionary and you find out what is a crystal, it's a transparent solid. Well, metallic crystals are not transparent to optical light, but they are transparent to other things. But it's too limiting. A solid bounded by plane faces called facets, that's too limiting, but it includes quasicrystals. So in this old definition, quasicrystals are crystals. A substance, solid substance made in which the constituent atoms or molecules are packed in a regularly ordered, repeating, 3-dimensional pattern. That was the definition. It's too limiting. It's long in use, excluded quasicrystals. It accepted a whole bunch of defects as parts of real crystals. There are 4-dimensional crystals called modulated structures in which you have a basic lattice and that's what made it acceptable in the old one. But then there would be a 4th condition, which was an order pattern or a magnetic order that was incommensurate with the with the crystal lattice of the atoms? Well, people could easily say, well, this is a lattice, this is a crystal which has a modulation on it. But if the modulation is not periodic, I mean, it's periodic, but with a different periodicity, it became a four-dimensional crystal. It should be a four-dimensional crystal. So it could be subsumed into this definition. The new definition is a solid having an essentially discrete diffraction pattern. And this is new, and it includes quasi-periodic materials as well as some disorder. And this came from 1992, and this is its actual thing. So, let me conclude then. Quasicrystals have enlarged crystallography. It is a revolution. They could not be included in what had been crystals before, but there are new opportunities. There are new properties. There are all kinds of crystals. Instead of having that limited number of structures, we can now go to a much larger number of structures. What came before is not discarded, because you instantly know whether you have a periodic crystal. You have a reciprocal lattice, which tells you that the actual structure is a lattice. You have symmetries that do not include 5 and 7 and up. So you know when to watch out. Just like in quantum mechanics or in relativity, you know that now you can't apply Newton's laws. If things are going too fast, you better do it relativistically. So there's no danger of being wrong. Periodicity in higher dimensions has been added, and that's apparently also very important in IT, because people worry about storage capacity, and often they look at their storage capacity as being in a higher dimensional space. There's a new interest in ordered periodic and ordered periodic patterns in many dimensions, and art, architecture, and music have become conscious of quasiperiodicity. I forgot to mention there are now compositions in which the measures are quasi-periodic. The measures is another periodicity in music. And of course, tonal things have long been quasi-periodic, but even having variable measure lengths I've heard the music. It's too modern for my taste, but it does exist. So that's it. And I want to thank the Inamori Foundation and Dr. Inamori for